Welcome to breadboarding. In the previous video we managed to get the Breadboard PC CGA card here, so this is a video card, to work in text mode, and this is just one of the example screens we have from the test program, but I didn't have time to get it running with the BIOS and do a few other checks and things. So this is Breadboard PC 8088 version 2, and this is video 17, in which we're going to be looking at tweaking the BIOS, checking the real-time clock and doing a few CGA video tweaks. This is just revisiting the BIOS section, and we're also going to be doing a few tweaks to the CGA video configuration in advance of looking at the floppy disk controller. So in order to boot the BIOS with CGA video, we also had the serial output enabled in the earlier video, so in order to test that the basic power on self-test operations for the timer and the interrupt controller were working, we actually had serial output, so we want to disable that. But also, when I was doing some investigation, it looked like the CGA status wasn't being polled by the video BIOS waiting for the blanking periods when display enable is low. So there were a few things I need to look at there. There was also some corruption on the BIOS power on self-test page, which didn't really appear with the CGA test program. Perhaps one or two blocks would appear, but it wasn't really a problem with the test program, but was with the BIOS. And so I'm going to be reconfiguring the BIOS to disable the serial output and doing a few other tweaks and things whilst we're doing it. We're also going to be looking at the real-time clock to make sure that's working, in particular setting the date and time and disabling the floppy disk drives, making sure the CMOS configuration is backed up when it's powered down. So I've added a backup cell to the CMOS clock, and I've also enabled this RTC auto detect. So as I was troubleshooting this, what this does is tries to read back the configuration of the control register in the real-time clock. If it can't read it, then it says that it doesn't exist. So that helped me to diagnose this problem here, in that there's a data bus buffer that we added a number of videos ago, but I'd actually missed out some of the real-time clock terms which provided the output enable of this buffer. So we'll look at a few things there as well. So this is the BIOS output that I was seeing. So you can see along the top here, there's various missing letters, and you can also see some of the attributes as well are also getting corrupted. So this obviously took me a little while to get to the bottom of, and I suspect it was partly to do with the video write timing. So we'll be looking at that in a minute, but it was also turned out to be also the clock that was used for the address latches also needed to be slightly delayed. And checking out the status register, so these are the values in the status register we expect. F4 when neither of the horizontal or vertical sync periods are, F5 when bit 0 is high, and FD when both 0 and 3 are high. So this is how we can tell whether we've got the vertical sync period or just the blanking period at the end of each line. And I did check this out, and you can see here that we've got the vertical sync and horizontal sync here. So this A1, A2 shows that we've actually got a value, quite small here, but F4, which is the first value it expects. This is outside of any horizontal sync, vertical sync, display enable period. Then F5 here, and then this is actually where we have the vertical sync starting. You can see we've got FD there. So there was no problem, in fact, with the CGA status. It turned out there were some problems in the enhancements I'd done on the MDA side of things. And in fact, the code that I had originally in here was reading the video mode within each check here. Unfortunately, the video mode assumed that the data segment was currently set to the BIOS page. And in fact, I then realized just down here that in fact the data segment was actually changed to the video page. So I was always looking up the byte from the video RAM rather than from the BIOS configuration. It just so happened that by default this is always actually set to 7, which matched the MDA. So that's quite a tricky one to get to the bottom of. Basically what I found out was that the BH register was not actually in use, so all I do is actually read the video mode when the data segment is actually set correctly, and then we can just compare the BH register to MDA. And the reason why I wasn't seeing the status being polled is because it thought it was in MDA mode the whole time, even when the CGA was shown on screen as working. So that was quite a tricky one to work out. Didn't really affect the video output much, but it was one of those sort of things that if things are not working properly, then that could be a cause of the problem. You can also see here that I've now defined a serial TTY output. So if you ever need to enable serial output of the BIOS, then I just comment this back in again and it will re-enable the output of all the power on self-test messages to the serial port. And can see also that we've got this RTC auto detect, and all this does is checks to see that the RTC is there by reading the control byte value that it sends out. And this is how I was able to test that the system buffer wasn't working properly. So that's all now been programmed, compiled and programmed, and I'm then going to show the other problems that I was running into for the video timing. So I was looking at the video write enable, and you can sort of see here that this is the write enable period here. And I tried during the memory write pulse up here, you can see that I was trying various ways using the various signals here, clock 88 signal that we were talking about in the last video. And although that did make some difference, it still ended up with blips. And you can see here, this one was even worse. Another one here still had this here, and another one here. And I even started to use a dot clock, and it all became very messy. So what I decided to do is to add some of the anti-snow changes that I'll be looking at in future videos. So I added this dot clock count. So this basically counts the number of dot clock cycles from the beginning of the read or write pulse. And all I've done now is said, right, we will do the write enable pulse on dot clock cycles 4 or 5. And so this now means that the write signal here is right in the middle of our memory write here, and so it's unlikely to interfere with anything else. And the other issue that I did run into as well, so even once I'd fixed that, there were still some problems occurring. And in fact, what it turned out is that there's the address latch clock down the bottom here. So the address latch clock down the bottom here, and originally this was actually timed to start at this point here. But in fact, there are some occasions where the address up here was going up in 2, so it goes up in the even addresses for the character byte, the odd addresses being the attribute byte, but occasionally this address had not stabilized, and so it would have some sort of more random address in here, and that's when the corruption would occur. And so all I did is change the address clock signal here to be delayed slightly, so you can see up here it's delayed by a bit of something like one and a bit dot clock cycles. So by delaying this signal slightly, it means that the address lines have stabilized before they get latched, and so this has actually fixed that particular problem. Now let's take a look at the board. So I've got the video capture on the left-hand side here. So it looks a little bit messier because I've still got all of the logic analyzer cables plugged into the center here. And you can see up on the top right-hand corner here, I've got the oscilloscope probe is on the real-time clock input. So we're just going to power it on. You can see it's coming up in the nanocomp monitor there. Now we're just going to press B for boot. The power on tone. And then we can see that it's now actually come up, and if we go to full screen, you can see here now that we don't have any corruption now. It is saying the real-time clock has got some sort of random looking date, so there's a bit of FF25 there. So the real-time clock is still counting a little bit in the background, but I don't think it's quite right, so we need to set that. So I did reset the CMOS back up just before I ran this. So you can see here as well, it's got the defaults here, so it says I think it's got a floppy drive that we haven't at the moment, but it has detected the serial port. So this is looking a lot better than it was previously. If you think of the previous slide where I included all of the missing characters and some of the attributes and things. I'm just going to reboot this now, and we'll press F1 as we go into the setup utility. So now type H for help and get a bit of video snow there. So we're just going to turn off the floppy disk drive. And so we'll say it's not installed. Now print out the configuration. Now I can see that the date and time is probably not quite right, so I'm just going to go in and set that. just set the time as well. We'll just write that and we'll reboot it. So you can now see that Harris designed RTC 88, no mass coprocessor. We have a real-time clock, it's now got the correct date and time. It's detected the color graphics array 80x25 mode that we're in. We don't have a mouse connected at the moment. It's detected the COM1 serial port. At the moment we've got no drives configured. It's detected the 640k of RAM. So it looks like this is all pretty much good for what we need to go forward. So the only thing I'm going to do now is to just check to see that the RTC clock has not got any interference on it. In the version 1 Breadboard PC, one of the things I looked at doing better was that the crystal for the real-time clock, when the power's off, there's a fairly smooth clock signal here. When the power's on, you can see there's a bit of interference, and this actually caused the real-time clock to run a bit fast when the power's on. So we just wanted to check to see what the real-time clock signal looks like with the power on and also with the power off. So this is the real-time clock with the power on. You can see that there is a little bit of interference on there, but it's much cleaner than what we had previously. And if I just turn the computer off, you can see now that we get the clean signal. I turn it on, and then we'll boot it up. You can see that we've got slightly more noise on it, but I think it's a lot cleaner than it was previously. So that looks good. So I will try that out and see whether or not we lose any time or gain any time when the computer's running and when it's off. So that looks good. Now take a look at some of the fixes I've actually done here. So on the PLD configuration, there's a few more changes I did over the previous time. We added the clock 88 to try and fix some of the video write enable clock timing issues last time, but now what I've done is added some of the video snow enhancements. So this is a dot clock counter which counts the number of dot clock cycles from the beginning of a read or write pulse. The address clock, last time we changed the polarity of that. Definitions, and you can see here that we've got a dot clock cycle which actually allows us to look at any one of the 0 to 15 intervals from the start of the read or write pulse. The high-res flag I've now set to default to 1. These are some of the settings that we used in the previous time, and I've done a number of different trial and error changes that we'll cover in a minute. Then the address clock here, the change here has moved the address clock pulse back a little bit by about 1 dot clock. So the CPU activity here is based on the CGA RAM and either a read or a write, and then it's delayed by 1 dot clock, 25 megahertz dot clock. And you can see here that we then reset the count on here every time we get some new CPU activity. So this basically gives us a count of the dot clock cycles during a write pulse, and by setting it to, you can see here, by setting this to dot clock cycle 4 or dot clock cycle 5, we're able to make the pulse about halfway through the memory read-write cycle. If you have a look at the logic analyzer here, you can see that this pulse here is the width of about 80 nanoseconds. If you look up the top right hand side here, width of 80 nanoseconds, which is approximately 2 dot clock cycles, and is bang in the middle here. And also you can see there the delay to the address clock, which has actually fixed that particular issue. And then the other problem with the real-time clock was that this system buffer, the bidirectional buffer, the output enable term was incorrect and missed out some of the terms for the real-time clock. And you'll see here that I've had to swap the system buffer, chip enable, and the real-time clock address enable around, and I'll explain why that is in a minute. So the pins are for those to have swapped around. And you'll see here that by adding these additional real-time clock address enable, real-time clock write, and real-time clock read signals, then this has now incorporated the activity that needs to enable this buffer. Unfortunately, when you then compile that with the pins in the original place, then there were too many terms for this particular pin. This would have been, I think, pin 14 out on the edge. And when you look at these chips, then the outer pins can only have about 8 terms, where the inner pins will have between 12 and 16. So by moving these 2 pins around, then we've got enough terms here to be able to do that. So I've done the wiring changes for that and programmed that, so that's actually fixed the real-time clock as well. That's tidied up a number of things, so getting CGA working with the BIOS and a few of the video controller tweaks as well. In the next video, we're going to be looking at the floppy disk controller and booting MS-DOS. So now we've got our BIOS working, we should then be able to see the messages to do with the floppy disk drives. We're also still going to be using the power on self-test port to actually provide diagnostic messages from the floppy disk BIOS code. But we should be in a good state now to get the floppy disk controller working and booting MS-DOS. So if you don't want to miss out on future videos, then please hit subscribe. If you could hit like, please, it just helps to make the videos available to more people. Thanks for watching.